This video is about half-angle identities, and to develop or show where these come from, we're actually going to start with some of our double-angle identities for cosine. So let's recall a couple of those, namely that the cosine of 2a, remember this one has a few different options, we're going to pick on a couple of them. One of those is cosine of 2a could be equal to 1 minus 2 sine squared of a. And another option I want to write up here, remember cosine of 2a has three different options. One of the others would be cosine of 2a could be 2 cosine squared of a minus 1. Now we're just going to adjust these given identities and solve each one of them for the squared part that's in each one. So for this first identity, I want to try to get sine squared a alone. Some of the algebra would involve a few steps of moving things back and forth, but ultimately I could end up with getting this term alone, and if I did, I would have 2 sine squared of a equals, and then the other side would end up being 1 minus cosine of 2a. Okay, so I left off a couple of the algebraic steps there, but you could try that on paper. It's only maybe a step or two to get 2 sine squared a alone. If I did, I'd have 1 minus cosine 2a on the other side. Now, if I divided by 2 on both sides to get this 2 out of here, I'd end up with sine squared of a alone, but then the other side would be 1 minus the cosine of 2a all over 2. And then lastly, to get sine a alone, I could take the square root of both sides to get rid of the squared, and if I did, I'd have sine of a equals plus or minus, and then we'd have the square root of this huge fraction that we already have here, which is 1 minus cosine of 2a all over 2. So all of that is underneath the square root, and now we've solved for sine a. But then, here's the somewhat tricky part. I want to get a half-angle formula out of this, and actually notice this 2a over here. It's kind of already there, but it's harder to see. So we're going to use a little substitution and say this. Let's let a be equal to x over 2. Now, what is x over 2? Well, it's just some angle divided by 2. And so this substitution is legal as long as we're consistent with it. And we'll do that, so I'm going to rewrite this last step we had, which would be now sine of, instead of writing a, I'm going to write our substitution and make it x over 2. And then I'm going to go to the right side and say that's still plus or minus square root of 1 minus cosine of, now instead of 2a, okay, well, if a is x over 2, then 2 times x over 2 would be just x. And that is all still over 2 underneath the root. And so this right here ends up being our half-angle identity for sine. And that's where it comes from. Now, we can do the same thing on the right side here with the other identity for cosine 2a. So we'll take some similar steps, and we'd want to get cosine squared of a alone first. Again, just take a couple steps of that. You'll end up with 2 cosine squared of a equals, this time it would be cosine 2a plus 1, just by adding 1 to both sides really there. Then we could divide by 2 on both sides, which would give us cosine squared of a equals cosine of 2a plus 1 all over 2. And then we could take the square root of both sides, which would give us cosine of a equals plus or minus, there it is, square root of this whole fraction. So that's cosine of 2a plus 1 all over 2. Now we're going to do the same little substitution. I'm going to say here, let a really be some angle that's cut in half, so x over 2. And therefore I can rewrite this as cosine of x over 2, that's just replacing the a we had here, equals plus or minus square root of cosine of, now instead of writing 2a, if a is x over 2, 2 times x over 2 would be just x plus 1 all over 2. And so this would be the half angle identity for cosine. Again, they're called half angle identities because they're when you have an input of something divided by 2. So x over 2 is the input in both cases. Now before we move on, I want to take just a moment to remind you or show you where you can get a handout on D2L of these identities and even the previous ones, which were the double angle identities. If you look at our content section in D2L and then click on the materials tab, you'll see plenty of things we've been using already, all the other identities earlier from chapter 4. And then you'll notice now somewhere near the bottom a file called 4.4, 4.5 identities. If you take a look at this one, you'll notice, first of all the double angle identities that we did in the previous video are there in all their forms. And then the half angle identities, we've just shown where 2 of them come. Now, if you look at the right sides of these are the 2 that we just developed, sine of x over 2 and cosine of x over 2. Notice the plus or minus and then the root. That's exactly what we just did. You'll notice, though, next to them are some equivalent forms, but these are when they're both sine squared and cosine squared. Both forms of these are in the textbook, so I have them both here on this sheet, but really they're one and the same. If you take what we just developed on the right sides here and, for instance, squared both sides of the equations, you would get the left identity that you'll see here. So that's how closely they are related. Or similarly, if you start here on the left sides of these and take the square roots of them, you'll get what we have on the right sides, which is actually part of what we did when developing them. Now you'll also notice a third option down here for tangent of x over 2. This is the half angle identity for tangent. Notice, though, it has 3 different options. So these, though you'll want to know them all, will not always all be used at the same time. We'll just have to pick and choose whatever is convenient, as you'll see in some examples here shortly. These identities for sine, cosine, and tangent will cover the half angle identities that we'll need. And of course, all of these should be memorized, and as you use them, that should start to happen with practice. Let's take a look at an example now that will help use some of these identities we've been learning. And let's take a look at an identity where we want to prove that, as it says here, the tangent of x over 2 times the tangent of x is equal to the secant of x minus 1. Now, as we know by now, with these prove or show problems, we're trying to show that this is true. We can't assume it is from the beginning, which means we want to work from one side to the other, or maybe find a way to connect these two sides using equivalent statements. Now, our practice so far has been to start with the more complicated looking side, and again, sometimes that's debatable, but I think it's fair to say in this case that the left side of this identity is probably more complicated. It has a product of terms, and it includes a half angle identity. So let's go ahead and start with that one. I'm just going to copy it over here. So we'll have tangent of x over 2 times tangent of x. And then we want to start now replacing or substituting equivalent statements to turn this into the right side of this equation or identity. Now let's start off right away, of course, with this half angle identity for tangent. You'll recall, if you look at the handout on D2L or any notes you might have taken from it, you'll notice that there are actually 3 different options for the half angle identity for tangent. Sometimes it's not clear which one you should use, so you might have to just try something and see if it gets anywhere good. If not, back up and try a different one of those. But in this case, let's see if we can use the identity that would turn tangent of x over 2 into 1 minus cosine of x all over the sine of x. You'll notice that is one of the options for the half angle identity for tangent, and we're going to just try it for now. Now, of course, we're still multiplying this times the tangent of x, and so let's go ahead and see why I might have picked this particular option for the half angle for tangent of x over 2. Now, notice it's 1 minus cosine x over sine x. What is tangent of x, this next factor? Well, we know, let's say these are all equivalent. I'm just going to copy this all down again. So I have 1 minus cosine of x over sine of x. But tangent is really sine of x over cosine of x. That's kind of old news by now. But notice how convenient it is to have the sine x on the top of the fraction on the right and the bottom on the left, because those will now, in fact, cancel out. Now, that might be obvious as you're kind of surveying which one to pick for tangent of x over 2, or maybe it wasn't, but at least now you can see why we might be motivated to pick this option for the half angle of tangent. Now, if I leave the rest of this going, I'll have 1 minus cosine of x over now just cosine of x. And then if I split up this fraction, as is one of our strategies, this would be the same as 1 over cosine of x minus cosine of x over cosine of x. And then just a little bit of simplification would turn that into 1 over cosine is secant, so secant x minus cosine x over cosine x is 1. And that's exactly where we were trying to end up, if you look at where we started, so we'll finish with that. Let's take a look at another example where we want to prove an identity. This one is prove that the tangent of a over 2 times the sine of a is equal to the tangent of a minus the sine of a all over sine of a times secant of a. Alright, now as is our custom, we're going to try to pick the more complicated side, but I purposely wanted to show this example because I don't think it's super clear which side is more complicated. They both don't look that great. So I'm going to show you an example of how you can actually work on both sides with an identity, but to do so, and this works really with any of them, but especially when both sides are looking pretty ugly and it's not clear which one you want to start on. To work on both sides, a major recommendation I'm going to make is that we actually draw a huge dividing bar right through the equal sign that's going to cut our paper in half. The reason we need to do that is because it's dangerous to be working on both sides at once. We can tend to try to slip into some algebraic practices like clearing fractions or operating as if we know this is an equation, but we don't know it yet. So if we're going to work on both sides, that's fine, but we have to keep those sides to themselves until the very end. Alright, now let's take a look at what we could do maybe on either side. If you look at the left side, there clearly is a half angle identity to begin with right here, and it's tangent of a over 2 times sine of a. So if we look at the second factor, sine of a, that's really a sine of a over 1, and isn't there an identity for tangent of a over 2 that would give us a sine of a in the denominator that would then maybe cancel with that one? Yeah, I think that's the one we used last time actually. So if we turn tangent of a over 2 into 1 minus the cosine of a all over the sine of a, that just being one of the options for tangent, again see the identity sheet for section 4.4 and 4.5, you'll see the options for tangent on there. We're just picking one of those options, but I'm going to keep now multiplying by the sine of a, which we had there. Of course, those sine of a's will cancel, so that's good news. Now let's go to the right side before we get too far on the left. In fact, we may not know what to do next, but let's go to the right side and see if we can take that a step or two. And to do so, let's just try converting all these tangents and secants into what their equivalent forms are, which is tangent of a is really sine of a over cosine of a. So I'm going to replace tangent of a with that, minus, now we already have a sine of a on top there, and that's all over sine of a times secant of a, which is really 1 over cosine of a. Now, anytime we have a complex fraction, which is when you have fractions within a big fraction, as we've seen before, so it's often nice to reduce that, and one good way to reduce a complex fraction is multiplying the entire numerator and entire denominator by the, well, common denominator of the little denominator. So there's a cosine a here, up in the numerator, this cosine a, and then down our second denominator factor down here is also a cosine a. So that's going to be my choice. If I multiply by cosine of a for the entire numerator and denominator, I'll be distributing this cosine of a to each of these terms in the numerator, but now notice below This operation here, this was multiplication, which means we don't actually distribute the cosine of a because these are not even separate terms. They're factors connected with multiplication. So if we take a look at what we'll have at the next step, on top, if I distribute the cosine a to these two terms in the major numerator up here, the cosine a's will cancel in the first term, giving me just sine of a. In the second term, I'll have minus sine of a cosine a. And then down below, remember this is not distributing now. This cosine a is really cosine a over 1 outside here. So that cosine a would cancel with this one, leaving us just with a sine of a in that denominator. Now let's try to take this a step further before we try to match it up with the left side here. Notice that it's a couple terms over one denominator, so we could split these up to make this sine of a over sine of a minus, and then the second term up top, sine of a cosine of a over the denominator sine of a. And now we'll just reduce. Let's just keep this side going for a minute here. These sine of a's will cancel, giving us just 1 minus, and then these sine of a's will cancel, giving us 1 minus cosine of a. But now notice, that's pretty much where the left side ended up. So if we could just kind of bring that side down and copy what was left there, it was also 1 minus cosine of a. And so since both sides now match, we can say we're done showing this identity. So here's an example of not only using the half-angle identities, but also working on an identity proof with both sides at the same time. When both sides become exactly the same, you know you've shown it or proven that this is true.